Hi everyone, welcome to second video of greedy radar series. In this video we will learn about greedy stage ahead technique which is used for proving greedy algorithms. So for this video the table of contents will be first we'll go through general working of PMI which stands for principle of mathematical induction. Then we will go through general working of greedy stage ahead and then we will see an example of greedy stage ahead. Now why we are doing this PMI here, it's because this is a prerequisite for greedy stage ahead. If you don't know about PMI we won't understand greedy stage ahead. Yeah, so let's start with the PMI first. So PMI, so here we first prove something for the base case, prove something for the base case, and then we assume that it is true for x equals to k, and then we prove that it is true for x equals to k plus 1. So like how this works is, if we prove something for base case then and we prove this true also, then we can if base case is true we can say that k 1 plus 1 that is true is also true, next case is also true, and similarly next and next case will also be true. So this is the general working of PMI. Now let's see a very simple example. So let's say we have to prove this statement with PMI. So the statement is, we are given n nodes and with n minus 1 edges. All are connected. So prove that this is a tree. Prove that this is a tree. So we have to prove this statement here. So first let's assume the base case, let's prove it for base case. So we can assume the base case is maybe the number of vertices equals to 2 and edge is equals to 1, and all are connected, so there can only be one edge between these two vertices, and this is a tree since it doesn't have a cycle. So this is the base case. Now case k, here n equals to k and e equals to k minus 1. Here assume that it is a tree. Assume it is a tree. And then we move to case of k plus 1. Here n equals to k plus 1 and e equals to k. Now we know that from case k we can move to k plus 1 by adding one node and one edge, right? Equals to k and n equals to k plus 1. So, and we also know that let's say there is some set of nodes whose cycle is just about to get completed, and here let's say we have to add some edge, right? So if we add some edge we can only add one edge with one node, right? So this requires at least two edges with one new node to form a cycle, and we are saying that we will add only one edge with one node, so it is impossible to create a cycle. So it is proved that this is a tree since it doesn't have any cycles, right? Yeah, so this is the very simple example for PMI. Now we can move ahead to greedy stage ahead technique. Yeah, greedy stage ahead. So we'll go through simple steps first, like steps. Step 1 is label your algorithm and a general solution. So for example, let's say our algorithm gives us the solution of a1, a2, ak, right? And any optimal solution gives solution like o1, o2, dot 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 o of m. So this is how we can label our algorithm and a general solution. So this comes from our algorithm, from the greedy algorithm, and this comes from, this is like any general optimal solution. Now the ordering in the A will be according to our algorithm, right? But the ordering in O will be such that um, these two things, ordering and measure, go hand in hand. So in greedy stage ahead we also choose a measure. So these two things goes hand in hand. We'll understand more about this with an example, but first let's write all the steps. Second step is find a measure. So here we define a measure f of something, right, by which greedy stays ahead of the general solution, right? And here the example can be like f of a1, a2, a of j can be some measure. Like here it would be maybe last completion time of first j events, right? Or it can be something like total weight of for first j nodes, or maybe it can be largest index of first j characters, anything. So we choose some measure and work on it. Similarly we define f of o1, right? So we define these two, like this measure for both our algorithm solution and the optimal solution, like om, oj, like this. So second step is about finding a measure. Now the step 3 is we prove that greedy stays ahead. So here we show that the partial solution constructed by our algorithm always stays ahead in this measure against the any general solution. And fourth and final step is prove optimality. And the third step we generally do by induction. Use induction here. And the final step is prove optimality. Here we use this measure since it was staying ahead of the any general solution, and use that to prove optimality. Yeah, and the main challenge here in this technique is to pick right measurements, because if you don't pick right measurements we might not be able to prove our algorithm here. So to arrive at a solution faster, to arrive at a proof faster, we generally perform the second and fourth step in combined, and then we go to the third step. So this makes it faster to choose the measure, so that we can be sure that this measure can be used to prove the optimality, and then we can move to the step 3, which was greedy stays ahead. Because think about this, let's say we choose some measure and we move to step 3 first, and it takes a lot of time, and then we move to fourth step and we see that we can't use this measure to prove the optimality, then all our work goes to waste, right? So we always do this fourth step with the second step by assuming that step 3 will works fine, right? Yeah, so these are all the steps for greedy stays ahead technique. Now let's see an example. So for example we will see the interval scheduling problem. Here first let's see the problem statement. So the problem statement is given starting and ending time of events like s1, e1, s2, e2, right? Similarly we can go on to sn, en. So these are the starting and ending time of n events in this problem, and we have to find max number of events we can attend without any conflict. So what this means is we can't have any overlapping events. For example, let's say some event goes from 1 to 5 and we attend this event, then we can't attend any event which overlaps with this event. For example, 2 to 6. So we can't attend this 2 to 6 event, and this one we can attend. Yeah, so this is the meaning of attending events without any conflict. Now let's try to solve this with greedy solution. So we can sometimes guess the greedy solution for the problems. For example, first we can try to choose events based on starting times, right? Second, we can try to choose events based on increasing lengths. And third, maybe, and third can be like try to choose events based on increasing ending times, right? So we can try all these approaches, and whenever we want to see that if this is the correct approach, we often try to like come up with the worst cases that this will fail. For example, in the first one, we are saying that we will choose events based on start time. So we can choose, like we can create some case here. For example, we have some events like this, and there is event here whose start time is the earliest. So according to the first approach, we will choose this event first, and this will go on until this point of time, and we won't be able to choose these events in that case. So this returns a bad solution, because here we can clearly see that if we choose these two, we will have the answer as 2, but according to this approach, we are choosing this event which is returning just 1. So this is not a good approach, right? Second, we can try to choose based on increasing lengths. So here also we'll try to create some conflict, like let's say we have two events like this, and there is a very small event which appears like this. It is overlapping with both of these events, and here we can see that according to this approach, we will choose this event first, right? And then we won't be able to choose these two, and we also know that if we choose these two, we will have the answer as 2 clearly, but according to this approach, the answer will be 1. So this is also not a good approach. And third, we can try to like make cases where it won't be true, but I know that since I know that this is a correct approach, I won't be able to find uh, like the conflicting examples here. We can try many examples here, but I know that we won't be able to find, so I'll just move ahead with the proof here. Yeah, so let's try to prove the third option. So step 1 is label solution, right? So first step is label solutions. So we can assume that the solution returned by algorithm is a equals to I1, I2 up to Ik, and we can assume the any optimal solution equals to J1, J2 up to J of m. And here we have to assume the order, like in this algorithm, the order is like these all are ordered by ending times, right? Increasing ending times. And here we can whatever the order we choose these m events in, but we will order them according to the ending times. Order according to ending times. Like this makes our proof easier. Yes. So we can move to step 2 now. So since I told you that we always perform step 2 with step 4, so we'll name it step 2 plus 4. So here we find a measure plus prove optimality. So this is the second plus 4 step. So let's say after x events are added, we define measure as last finish time of events. So f of I1, I2 up till I of x will be equal to E of Ix, right? Ending time of this event. And similarly, f of J1, J2 after x events will be equal to E of Jx. Now we will try to prove optimality with this measurement. So to prove optimality, we often use contradiction method. Contradiction. So let's say we assume that k is less than m, right? K was coming from our algorithm like here, and m is coming from any optimal solution. So let's assume that k is less than m, and we know that in our measure, actually I forgot to tell you that we are using this property here, that E of Ix is less than equals to E of Jx. So this we will have to prove in step 3, but we assume that this is true for now. Assume it is true. So in greedy stage ahead, we find some measurement and we try to prove like the order, or we try to prove that this measure is staying ahead in each step. For example, in this case we assume that the ending time of x activities is always less than equal to ending time of x activities from any other optimal solution. So this we will have to prove, right? Now this is a measure, and we are saying that our measure will hold this property, which we'll have to prove in step 3, but for now we can assume that this is true. So let's try to prove optimality now. So we assumed that k is less than m, so this is proved by contradiction. So now we know that f of ik is less than equals to f of jk, right? J is the optimal solution and I is the like our algorithm solution. And also we know that s of jk plus 1 is greater than f of jk. So this is the starting time of the jk plus 1 activity or event. So like this should be greater than the last event ending time, otherwise we won't be, we don't have this event in the optimal solution. So we know about these two properties here, right? Now if this is true, so we can add this job to our algorithm solution. Our algorithm solution will take this automatically, because we are saying that according to our algorithm we always choose the next earliest ending time event, right? And this starting time is greater than this, because this is greater than fjk is greater than this, and this is greater than f of jk. So we can definitely add this jk plus 1 event in our algorithm, and our algorithm will pick at least this event, maybe better than this, but at least one more event. So we have proved that our algorithm has not ended, and this is a contradiction since we assume that uh, k is less than m. So we can go on until k becomes equals to m. So this is a contradiction, right? Why it is a contradiction? Because we assume that k is less than m, and if k is less than m, we can always say that there is one more activity that we can add to our algorithm, and our algorithm will not end. So yeah, this is a contradiction. Now k becomes like one more than earlier, and this keeps happening until k becomes equals to m, right? So this is a step 2 plus step 4. Now we can move to step 3. In step 3 we try to prove the greedy stays ahead property. Greedy stays ahead. So we earlier assumed that this is true, e of ix is less than equal to true if e of jx. So now we have to prove this property. So let's start with the base case. Let's say we have k x equals to 1, right? Now when x equals to 1, we know that our algorithm will choose the event with lowest ending time, and whatever optimal solution chose, it doesn't matter, because we have chosen the earliest ending time event. So in x equals to 1 case, e of iz1 is definitely less than equals to e of j1, right? So this is the base case. Now we can move to x equals to t case. Here we will assume that e of it is less than equals to e of jt. Now we assume that this is true. Assume this is true. Now we move to x equals to t plus 1 case. Like here we need to prove that e of I t plus 1 less than equals to e of j t plus 1, right? Now how can we do this? So we know that this is true, right? And we also know that s of jt plus 1 is greater than e of jt, right? So we can definitely add this event in our algorithm solution, and we will choose better, in fact, like we will choose the event with least ending time possible. So whatever the ending time of this event is, our algorithm will give us better ending time, because we will choose at least this and or better one, right? So we have proved that e of I t plus 1 less than equals to e of j t plus 1. So this we had to prove. Now the proof is complete. since we already proved that if this measure property is true, then we can prove optimality also, that our algorithm will always return the best solution. So yeah, this is all about greedy stage ahead technique, and we will go through more such problems where we can use greedy stage ahead technique in the upcoming videos. So that's it for this video, guys, and thank you for watching.